Okay, so now I want to turn from a single body, we've talked about the structure of a single body of some arbitrary shape, to the structure and motion of multiple bodies. Bodies made of perfect fluid that might be orbiting around each other, interacting with each other in some complicated way. Now, in general, this is quite a messy and complicated problem because, as you might imagine. But if you make some assumptions, then you can simplify the problem or structure the problem in such a way that you can make a lot of progress. And here are the basic assumptions that one typically makes when considering multiple bodies interacting with each other. The first, very important one, is that each body is assumed to be small compared to the typical separation between the bodies. So you can regard each body as some small object and the other bodies are distant. This is very nice because if the bodies are far enough away, then you just have an isolated body and you can figure out what its structure is. Maybe it's spherically symmetric if it isn't rotating, or it's just deformed if it's rotating. Maybe it's like the Earth, and it's alone. It's not affected by the other body if the other body is infinitely far away. But as long as the bodies are far enough away that this condition holds, then you can sort of treat each body as sort of isolated and then worry about how the other bodies interact with it. But here I want to talk about isolated also in the sense that there's no mass flow out of any given body. This is a non-trivial statement because there are binary star systems, for example, in which there's significant mass flow from one star to another. This is called the Roche problem. The stars get close enough together that the gravitational field of one star can draw matter from the atmosphere of the other, and there can be significant mass transfer from one body to another, which really affects the dynamics of that simple two-body system. The dynamics becomes very complicated when you have this kind of mass transfer. So we will avoid dealing with those kinds of issues, and we'll assume that each body really is isolated, its mass really is constant, no mass flows from it. We will also assume, and this to some degree follows from this assumption, to some degree, that there are two timescales involved in these kinds of problems. One is an internal timescale. It's roughly speaking, it is proportional to the cube of the radius of a given body over g times its mass to the square root. That's sort of an internal time scale. Roughly speaking, that's the period of oscillation of such a body if it were induced to oscillate by some external force. So that's one time scale. Then there's another time scale, the orbital time scale, which you know from Newtonian dynamics is proportional to the cube of the, say, separation between bodies divided by gm, square root. And our assumption will be that the internal time scale is much, much shorter than the orbital time scale. So these bodies may oscillate, but that oscillation is rapid compared to, say, the orbital periods of the bodies going around. And to some degree that follows from this assumption, right? So R here is much, much less than R, but of course, since the masses of the different bodies are involved, it might be violated if you had some extreme mass ratios, but we'll assume that most of the masses are comparable. So it sort of follows from this, but it's an important criterion anyway because it allows you to view each body itself as in a kind of quasi-equilibrium state. You know, if one body passes by it, it might excite some oscillations in this body due to its gravitational forces, but those, because they operate on such a short time scale, those oscillations will damp out due to the natural dissipation mechanisms that are in any body, friction and viscosity and so on. Those things will damp out on a short time scale compared to the orbital one. So basically you can view each body as being in a kind of equilibrium state. It's not undergoing wild gyrations. Okay. So essentially what you're saying is that each body will respond to tidal deformations in a kind of adiabatic way. So a distant body causes this thing to be deformed due to the tidal gravitational forces, but that deformation goes adiabatically, slowly compared to the very short time scales internal to the body. It also allows us more or less to regard each body as nearly spherical so that we can use our multiple expansions earlier on. If a body is sitting alone and it's not too rapidly rotating, it's going to be nearly spherical. Maybe it'll be slightly deformed due to its rotation, and that's about it. So it allows us to use that almost spherical body formalism that we developed in the last lecture. And so these assumptions then sort of allow you to break down the problem of multiple bodies going around each other into two. First, an external problem. You determine the motions of the bodies as functions of the internal parameters. Remember, you don't have point masses anymore, right? When you had a bunch of point masses, it was kind of easy to determine the motions. Now you have a body, a bunch of bodies, and the nature of each body may depend on the location of the other bodies, because this body may deform this body because of its tidal gravitational forces, and this body may deform that body, and this body may deform that body. And so the motion of each body may depend on the detailed parameters of all the other bodies. But because we expect these deformations to be small, you first then determine the motions of bodies as functions, or maybe as functionals, as functions of other functions that you haven't yet figured out just yet, that depend on the internal parameters, like the multiple moments of each body. Then given the locations of these bodies, you've determined the evolution of the internal parameters. So as each body moves, as this guy moves to here, the deformation of this body is going to point that way. And so you figure out the changes in the shapes and the multiple moments of this body as a function of the motion of that body. The trouble is, you can see it's a very complicated interactive problem, and so to really get the problem, you either have to solve it self-consistently or iteratively. You do this, maybe forgetting about the multiple moments, then you figure out the multiple moments, then you take that and put it back into here, and you'll take the solutions and plug them back in until you get some kind of convergent solution. I mean, this is really a complex problem in a formal sense, but with these assumptions, because you make the internal properties rather minor, because you've made these bodies so small and so very nearly spherical, you can then kind of use a perturbation approach to solve these two problems and let them interact with each other. And a classic example of this is, of course, the Earth-Moon system. The Moon is in orbit around the Earth. The Moon raises tides on the Earth. I'm not talking about the ocean tides. I mean, they're there, but it also makes the solid Earth deform. The ocean tides are a minor bit of that, but the actual solid Earth deforms due to the Moon, and that deformation depends on where the Moon is. But now the Moon is moving in a field that is no longer that of the pure Earth. It's of an Earth that's been deformed by the Moon itself. And the multiple moments that the Moon has generated on the Earth change the gravitational field of the Earth and alter the orbit of the Moon. So the Moon is altered by the fact that it has deformed the Earth. So this problem then has to be solved in a kind of iterative or self-consistent way. And indeed, the Earth-Moon system is really a classic example of how these kinds of effects really change the dynamics. For example, we know the Earth is receding from the Moon. The Moon is receding from the Earth. It's getting further and further away steadily with time. That's because the Moon deforms the Earth, but this deformation of the Earth doesn't point directly at the Moon, as you would have thought. Why is that? That's because the Earth is also rotating. And so this tidal bulge of the Earth lags behind the Moon a little bit, and that's because the Earth can't respond instantaneously to the Moon's field because there's friction in the Earth. And you know, if you have any system with friction, there's a phase lag, if you know in electrical circuits, right? When you have a sinusoidal signal on a circuit with resistance, there's a phase lag between the response of the circuit and the driving signal. And that's caused by the dissipation in the system. So there's this phase lag between the bulge on the Earth. It doesn't point directly at the Moon. It lags behind a little bit. That's due to the fact the Earth is rotating. Well, that change in the field, this little difference in angle, the effect of that on the Moon's orbit is to make the Moon's orbit grow in distance, recede from the Earth. But also, the dissipation that causes this causes the Earth to slow down. Roughly speaking, the Moon raises tides of the ocean, say in the Atlantic Ocean, but I have to do it this way. Say in the Atlantic Ocean here, but the Earth is rotating to the east, so this big tidal bulge in the ocean hits the east coast of the United States, and that causes a little torque on the American continent that slows down the Earth. I mean, it's almost as simple as that. You can model this just by it's really dominated by the effects of the water tides that are big hitting the continental shelves. So that slows down the Earth. And in time, the Earth will stop rotating at all, or at least will stop rotating down to the level where it rotates at the same speed as the moon orbits it. So the Earth will be tidally locked relative to the moon. So one face of the Earth will always face the moon and just orbit like this. Now, in fact, this should be pretty obvious. In fact, this was already realized by the famous philosopher Kant. It was already known that the moon always presents the same face to the Earth, right? And Kant realized that this must have happened probably due to tidal interactions. Kant knew all about Newtonian theory. So if it happened to the moon, surely it's going to happen to the Earth. So Kant predicted that the Earth would ultimately become tidally locked to the moon, and they would just rotate like this, with the two faces always pointing toward each other, so there'd be people, assuming there are still people left then, there would be people who would never see the moon, and people who would always see the moon all the time in the sky, and they'd be tidally locked. This is an example of this coupling. The orbit of the moon it won't go to infinity, it'll reach out, its period will increase, it will get slower and slower, and it'll recede to some distance. By that time, the Earth will have stopped rotating, will rotate in lockstep with the moon, and all these effects will turn off. And then the two will just orbit each other forever with no further change. Except that ultimately gravitational waves will cause them to spiral into each other. But that time scale is so long, it's an exercise that you'll work on later on, that you don't need to worry about it. And you don't need to worry about any of this, of course, but it's an interesting story. So anyway, it can be a very complicated story dealing with the mutual interactions of these really physically finite-sized bodies. But I'm going to just develop a basic framework for doing this using the machinery we've talked about already. And then later on, as we go along, we'll be able to do some real examples of the consequences of some of these effects. So the idea is to take to consider a system of bodies, each body labeled by a label A. First thing is to define some variables that we want to associate with each body. So for each body, there'll be a mass, which is just the integral over each body of the density rho. And we know that that is conserved, right? Because just by our continuity equation, as long as this volume encloses the body and there's nothing flowing away from the body, then mass is conserved. We'll define a center of mass of the body, just as we defined a center of mass of the whole system. Here we'll define this for each body, integral of rho times the vector x integrated over each body divided by the mass. And using our rules of the road, again, always assuming these integrals enclose each body so that the surfaces are all in vacuum, then the velocity of each body with just dr dt, it's the integral over the velocity. The acceleration of each body, dva dt, is just an integral of dv dt, and then we can plug in Euler's equation for dv dt. Okay? So these are very simple definitions, but I need to make a few comments. We've defined this center of mass, and a big question is the center of mass unique? And the answer is, of course, it's not unique. I could define center of mass in an infinite number of ways. I defined the center of mass there to be the integral of rho x d3x. But here's another definition that's just as valid. Has the right dimensions, right? It's got dimensions of rho x d3x. This is the average density over the body. But I've got a rho squared. You'll get a different center of mass. Of course, if your body is spherically symmetric, the center of mass is going to be at the geometrical center. But we want to talk about general bodies that could have weird shapes. So in principle, this center of mass, depending on the shape of the body, could be different from that center of mass. But it's a totally valid definition. What you really want, the main thing you want from a center of mass is that it should not wander outside the body. I mean, that would be a little crazy, right? If you had your body and the center of mass of your body, because of some crazy definition, started to be over here. Your center of mass to stay somewhere inside the body. But the basic point is, there's no way to measure the center of mass of a body. We determine the orbit of Mars, for example, by bouncing radar signals sent from the Earth off the surface of Mars. They don't bounce off the center of mass of Mars, they bounce off the surface. But we use that information, the distance between us and the surface of Mars, to infer the motion of a fictitious center of mass of Mars that's constructed from all that data. Or we look at orbiters of planets. The orbiter of, there was the Magellan orbiter around Mercury. Not Magellan, anyway, orbit around Mercury. You track that orbiter, which is going around the planet, but from knowing the details of that orbit, you infer what is the center of that orbit, which you associate with the center of mass. But you don't actually measure the center of mass. You measure things like surfaces or orbiters or moons and stuff. So there's a lot of inference that goes on into determining what's the actual motion of the center of mass of the planet. So it's an object that's not really physically measurable. And furthermore, when you start to talk about general relativity, it's a quantity that's essentially almost impossible to define. And there have been books written on how to define the center of mass of bodies in GR, and it's really a horrible and complicated question. Why? Well, it's an integral over the density. Well, what density? In general relativity, there are lots of densities. There's the rest mass density. There's the density of rest mass plus other forms of energy, including gravitational energy, because all energy is mass too, right? I mean, there are different kinds of energy that you can associate with mass. In general relativity, here you're just taking this vector x and adding it up throughout the body. You can't do that in general relativity. You can't add vectors at two different points. In order to add vectors, you have to take one vector and parallel transport it through the curved space-time that is curved by the very body that you're sitting in, parallel transport that to the other vector, and then add the vectors. And when people have tried to think about this in the context of general relativity, it's just a horrible and complicated problem. So we don't worry about whether it's unique. The idea is to pick a definition of the center of mass that, again, at least doesn't go too far outside the body, but that makes the equation simple. And as long as you have a way, once you've determined where the center of mass, how that evolves in time, as long as your machinery has a way to translate that into the location of the surface of the planet where your radar beam is going to reflect, or into the orbit of an orbiter around that planet where your radar signal is going to come, as long as you can go back and forth between those two, then you have a way to determine the motion of the body. Okay, so these are the things you never think about when you're talking about these questions, but especially because of the difficulty of doing this in GR, I think it's important to emphasize that it's really just a convenient choice. And as we'll see, this in Newtonian theory, this choice is very convenient. And we'll, in fact, make a very similar choice in general relativity, or at least in post-Minkowski theory. We'll make a very similar, simple choice that just leads to simple results. But again, at any given stage, you can really translate it into measurables, like how long it takes a radar beam to go and bounce off the surface and come back. Okay, so with that definition then, we want the acceleration of the body A in our system. So we have this, we plug in the Euler equation. So the Euler equation says that we have the gradient of the potential, but the potential has multiple contributions. The potential in the Euler equation has a contribution from body A itself. So we have to integrate over body A. I'm going to put the MA over on this side. So MA times A is the integral of body A, rho d3x, times the gradient of the potential due to body A, rho prime, blah, 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 d3x prime. So that's the contribution due to body A itself. As we saw before, the pressure term goes away because we turned it to a surface integral. That goes away. But then, in the Euler equation, there's the gradient of the potential due to all the other bodies. So I have the integral over body A of the gradient of the potential due to all the other bodies, B not equal to A. Okay? Okay. Well, first of all, what's the value of this term? Maybe you have two choices, 0 or 1. What's the value of the first term? We've seen it already. 0, right? Because it's anti-symmetric. This is integral over body A alone. So symmetric, symmetric, anti-symmetric, so it's got to be 0. So we can throw that term away. And that's just, again, action and reaction. The body does not accelerate itself. It only gets accelerated by the other bodies in the system. Now what about these terms? This is some horrible double integral over body A and each of the other bodies. So let's remember that each body is small compared to the separation between the bodies. And so let's take x, that's a vector that resides in body A, and write that as the center of mass of body A plus a small x bar. So this is going to be the distance between the center of mass of body A. So here's x from the center of our coordinate system, and we're going to write that as RA plus x bar, okay? And x bar is going to be small compared to the characteristic interbody distance, that's by our assumptions. Okay, so each of this is small compared to that. And the x prime here, let's write as xrb, the center mass of body B, plus x bar prime. And let's define RAB just to be the vector difference between RA minus RB. So the vector pointing from RB, from body B to body A. And now we see we can do a Taylor expansion just as we did before. Expand x, x minus x prime over all of this in a Taylor expansion. And in fact, we could back up one and remember this is the gradient of 1 over x minus x prime. So if we pull the gradient out for a moment, we know what the expansion of 1 over x minus x prime was. We did it a few slides ago. Just plug it in. It's a double Taylor expansion, of course. We're expanding on both this x bar and x bar prime, so it gets a bit messy. But you can plow through all the details, and you end up with this equation. So this gives the acceleration of body A. The first term, of course, looks like what you would have gotten if you just had point masses, right? It's the mass of body B, the vector from B to A, the points from body B to body A with a minus sign, so it's attractive, over r squared. So there's the point mass, n body acceleration, if each body had no multiple moments at all. And then there are terms that are linear in the multiple moments. The sum begins at L equals 2. Again, there's no L equals 1 term because we've defined our center of mass in such a way that the multiple moment for L equals 1 just vanishes by definition. So everything begins at L equals 2. And you can see that there are a set of terms that involve the multiple moments of all the other bodies times gradients, L gradients of 1 over RAB plus another gradient, because we're looking at the acceleration, we're looking at the gradient of the potential. So there's L plus 1 gradients of 1 over RAB, and these are the multiple moments, the STF multiple moments of the other bodies. Well, that makes a lot of sense, because if each body is not spherically symmetric, if it has multiple moments, those moments will affect the motion of our given body, because the field is not just a spherically symmetric field of a spherical mass. It's got all these other bits due to the fact that this body has a finite shape, and therefore the shape of body B will affect the motion of body A. So these terms you would have expected. Then there are a set of terms that depend on the multiple moment of body A. That came from the Taylor expansion of x itself, about body A. Now you might be bothered by this. You'd say, well, wait, doesn't this violate the principle of equivalence? Because this says that the acceleration of body A depends on the structure of body A. Right? But it really doesn't. Once you appreciate the context of the principle of equivalence, I didn't really emphasize it at the time, the principle of equivalence is really a kind of limiting statement where you assume that your body is infinitely small compared to all the external gravitational forces. It's really a limit in the limit of very zero size. Of course, since these things are proportional to the size of each body to the Lth power, right, and L is 2 or bigger, then as you shrink each body, these terms will just get smaller and smaller, and they'll go away in the limit. So it doesn't violate the principle of equivalence in that sense. But it does say that the shape of a body depends on its internal structure. But you shouldn't be bothered by that. A cricket bat, did I use the right term? Bat? I mean, I know an American baseball bat, but a cricket bat will move in a gravitational field with a different acceleration than a cricket ball of the same mass. Why? The ball is moving like this, right? Moving around in the field of some distant body. But the bat is moving. This end of the bat is being attracted more strongly than that end of the bat, and that difference is not uniform. Remember, it's a 1 over r potential. It's not a linear potential. And so that difference really matters. And so this cricket bat will move on a different trajectory. Its center of mass will move on a different trajectory than the spherical cricket ball. So the shape of a body can influence its own trajectory, its own motion in a gravitational field. And it's just because the field is non-uniform. Okay, so that term should be there. And then there are terms that involve products of these moments. Moment of A, body A, multiplying moments of body B. And it's a double sum over all L. It's some horrible thing. Again, that shouldn't totally surprise you if you think in terms of electrodynamics and molecular physics, atomic physics. You know that in electrodynamics there are dipole-dipole interactions between charged bodies and uncharged neutral bodies. I mean, dipole-dipole atomic interactions are crucial in chemistry and other things. So interaction between multiple moments of bodies to change their motion is commonplace in fields like atomic physics, and of course that's because the effects are quite strong because E and M is a much stronger force. But in gravity, they're certainly there, in principle at least. But again, you remember we assumed that our bodies are going to be well separated compared to their size, and so again you can see that these are going to be smaller effects depending on the size of each body and how far apart they are. This is 1 over r squared, and here let's look at L equals 2. So this is 2 plus 1 is 3. This goes as 1 over r to the 4th. And this goes as the size of the body squared. So compared to the leading term, this is size of the body. Well, we can do it generally. This is the size of the body to the nth power over the separation to the nth power. So as L gets bigger and bigger, clearly these effects get smaller and smaller. And in practical cases, maybe you can get by with just the first few terms, depending on how deformed your bodies are. Okay, but that is a general and actually exact expression for the equations of motion of multiple bodies of arbitrary shapes in their mutual fields. The thing is, of course, I haven't told you what these moments are. These are some functions of time, but they will depend on what the other bodies are doing. And on the body itself, if it's rotating, there'll be some internally induced multiple moments, like on the Earth, but there'll be moments induced by the other bodies because of tidal interactions. Each body can deform the other bodies. So until I tell you how these things vary with time, you can't really answer the problem. And I can't tell you how these vary with time until I tell you how each body moves. So this is, again, how you need to do this in a either self-consistent way or a perturbative way, where you maybe start out ignoring these things, throw these away, get the motion of each body as if there are point masses, then ask, with those motions, how do these things vary? Then using those, resolve and get the small changes in the motions, etc. And here, let me just boil this down to a simple problem. And this is a problem we'll actually encounter specifically later on. A problem where just two bodies, a two-body problem, where only one of the bodies, here body 2, has non-zero multiple moments. Okay, so one of our body 1 will ignore its multiple moments. Maybe it's a satellite orbiting a planet. Well, satellite's so small it has no important multiple moments. Or it's a black hole orbiting a star, like in Cygnus X1. The black hole is so small it can be viewed as a spherical body with no important moments, but this huge star, of course, has lots of multiple moments. In fact, many moments induced by the black hole itself. So many applications of this very simple case. And so we have just a two-body problem. Let's define a relative coordinate, r1 minus r2. R is the distance between the two bodies. there's the center of mass of the overall two-body system. We'll define the total mass of the two-body system and the reduced mass. This is a quantity we'll see a lot later. The reduced mass of the system, M1, M2 over M. This will show up later on. But with those definitions, then you can show that the relative acceleration, A1 minus A2, is the usual Newtonian acceleration. M is the total mass of the system, so that's standard Newton if you had spherical bodies or point masses, plus terms, an infinite sum over L equals 2 to infinity, involving the multiple moment of body 2. Okay, so if body 2 has a non-spherical shape, then its moments will contribute to the motion of body A. And so this is a kind of equation of motion for each of the GRACE satellites that I was describing to you. And here are the multiple moments of the Earth that affect the motion of each of those satellites. Okay. And then you take the two satellites, you calculate the difference in acceleration between the two. This you know, you can figure that out easily. And the difference in acceleration will then depend on the small difference in this term between the two locations of the two satellites, right? One's at 1 r, one's at a slightly different r or a slightly different x. They're separated from each other. So this will be different between the two satellites. And so by measuring A and knowing their locations, you can start to measure these guys. That's more or less what this GRACE mission is doing in measuring the multiple moments of the Earth. So we'll use this later on when we, for example, talk about perturbations of orbits around a body like the Earth or the Sun with a quadrupole moment, L equals 2. Okay, now let's simplify it even further. Let's throw away all the multiple moments, and in some ways we're going back to undergraduate physics to go to the very simple two-body Kepler problem. So we'll ignore all those multiple moments. Either bodies are either purely spherical or maybe just point masses so small that all those moments are negligible. Put our center of mass at the origin. I've already defined these quantities. And then the whole problem reduces to what people sometimes call the effective one-body problem. It looks like a single body. It's a single effective body just given by the separation vector between the two bodies. M here is the total mass, okay? So it's really just the first term in this equation. All this stuff gets thrown away, all that stuff gets thrown away. And then for two bodies, we get that. Here, and I'm sure you've done this before, you can show from this equation that the energy is conserved, and it's given just by the sum of the kinetic energies of the two bodies minus the gravitational potential energy, M1, M2 over the distance. And by looking at this thing and how you've defined the center of mass and these relative coordinates, you can show that this is just the reduced mass times the relative velocity squared. V is just V1 minus V2. Okay. So here's where the reduced mass starts to appear in the two-body problem. The angular momentum is also conserved. You know this just because this effective one-body problem is spherically symmetric, so angular momentum has to be conserved just due to the symmetry. So the total angular momentum, M1, R1 across V1, plus the other one, that boils down to mu, the reduced mass, times R cross V. Again, you have to translate R1 and V1, R2, V2 into R and V, but that simple transformation can be done and gives you this simple answer. One thing you conclude right away from this is that the orbital plane in this two-body problem is fixed, right? Because this is a vector that's perpendicular to the plane. R and V define the orbital plane. This vector points out of the plane, and it's a constant. It's the angular momentum vector, and therefore the orbital plane is fixed. Well, that then allows us to rotate our coordinate system to make the orbital plane to be the xy plane, just for simplicity. And so we have the relative vector, a vector perpendicular to that, which is just the rate of change of this unit vector with respect to angle phi. Phi is the phase relative to the x-axis. So these two vectors then define for example, the velocity. It's just the rate of change of r times the radial direction plus r times the rate of change of phi in the perpendicular direction. The cross product is, you can show, is just r squared times d phi dt, and we know that that's constant. That's the constant angular momentum, which we'll call h. It's the angular momentum per unit reduced mass. Here I've taken out the reduced mass to make life simple. Okay, so d phi dt is this constant h over r squared. There's the velocity. And from this energy conservation equation, you can calculate v squared from here, plug it in, and then you can rearrange terms so that you discover a nice equation that relates r dot squared, to the conserved energy per unit reduced mass, and an effective potential that's a combination of the attractive gravitational potential, minus gm over r, and this repulsive centrifugal potential, h squared over r squared. Right? This just came from, when you squared v, that came from this bit, and the r dot squared comes from that bit, and you take that piece and combine it with gravity into an effective potential. I mean, you've seen this before, but it's worth repeating, especially if you want to think about orbits in general relativity. Diagrams like this are also very useful. And this then allows you to solve the problem completely by by what's called quadratures. You can reduce the problem from a second order differential equation to just doing integrals. This is dr dt squared. Take the square root. Then dt is equal to dr over a function of r, and then so that you can just integrate. You get t minus some initial time is equal to the integral from some initial r to r of this radial function, and then, at least in principle, your problem is solved. You can take that, the function of r of t that you get from that, although it may be an implicit function, and then from this equation, get phi as a function of time by integrating. So you reduce the problem to just doing integrals. They're kind of ugly to do in general, but it's a very simple problem. And you all know how to deal with this effective potential. Depending on your energy, whenever the effective potential is at a level where it equals this energy per unit reduced mass, r dot is 0, and that's a turning point to the motion. R dot may be negative, you're coming in. When it goes to 0, then you start going back out again. And so if you plot this effective potential, then depending on what energy you choose, you might get one turning point. Here, E is greater than 0. There's a 0 of energy. Those are called hyperbolic orbits. So the body will come in, reach r dot equals 0, and turn around and go back out. It will reach infinity with a finite velocity, because here E is greater than V effective. As r goes to infinity, of course, V effective goes to 0, but this is non-zero, so you'll have a finite velocity at infinity. So this corresponds to a particle sent in from infinity with a finite velocity. It comes in. Of course, there's non-zero phi dot. Phi is changing with time too, so it basically comes in, reaches a minimum separation, and then goes out with a deflection. So it's a scattering orbit with a finite velocity at infinity. There's a special case of a parabolic orbit, E equals 0, so it starts with 0 velocity at infinity. You sort of hold it at infinity and let it go, and then it comes in, scatters. Again, there's finite phi dot, scatters, goes back out to infinity. Turns out they're called this because the actual shape and space of each orbit is a hyperbola in that case, and a parabola in that case. That's actually an exercise in our book. And then there are cases where E is negative, where there are two turning points, an inner turning point and an outer turning point. And this corresponds to the famous elliptical orbits, bound elliptical orbits in the Kepler problem. So this inner turning point is called the pericenter, and the outer turning point is the apocenter, and the shape of the orbit is an ellipse. And then there's a final special case where the energy is such that you're sitting right at the minimum of this potential, and so the two turning points can coalesce into one turning point, so that this particle is at a perpetual turning point. R dot is 0, so it's a circular orbit. And that's the special case. This shows sort of the formal solutions, where you could get T and phi as in terms of R, but you can get more explicit solutions by, for example, of the orbit as a function of angle, by some nice tricks. Look at the radial acceleration, or just take d by dt of that energy conservation equation, either way. You get this equation for r. R double dot is given by that. And then you do this nice trick where you, instead of talking about d by dt, instead of worrying about the evolution in time, you worry about the evolution as a function of the angle phi. So d by dt is just phi dot d by d phi. And we know that phi dot is h over r squared. Remember, h is the conserved angular momentum per unit mass. So you can go from d by dt to d by d phi. And it's also useful to work not in terms of r, but in terms of 1 over r. It's just a trick. And using that, you can convert this equation into a very simple equation for 1 over r, d2 d phi squared of 1 over r plus 1 over r is equal to this constant, which depends on just the mass and the angular momentum squared. This is just a harmonic oscillator equation, right? So the inhomogeneous solution is just this constant, and I'll define that constant, h squared over gm, to be p. It's called the semi-lattice rectum. In this field, there are all kinds of names for these things that come out of the 18th and 19th centuries, and who knows where they got these names, but the names stick. What does semi-lattice rectum mean? I mean, I have no idea. But there you go, that's what it's called. So that's the constant part, 1 over p, that's this. And then you have the homogeneous solution. This is a harmonic oscillator, so it's just a sum of a sine and a cosine of phi with 2 amplitudes. Or you can write it as an amplitude of a cosine with a phase. So here I'm writing it with an arbitrary amplitude E and with a phase phi minus omega. So this is the phase, that's the amplitude. Because that's the homogeneous solution of this equation. And there we have a solution for the radius of the separation of the system of the two bodies as a function of this angle phi minus omega. This particular combination, phi minus omega, is called the true anomaly. Another one of these names. Who knows? If your orbit is elliptical, if energy is negative, then you can show that means that E is less than 1. And then when F is 0, or when phi is equal to omega, this is the biggest it can be, so R is the smallest, so that's the pericenter. So it's P over 1 plus E. So that's when phi is equal to omega. So that's where the pericenter occurs. And the apocenter occurs when F is equal to pi, or when phi is omega plus pi, and that's given by P over 1 minus E, because you get a minus sign. The sum of those two, or divided by 2, is called the semi-major axis, so it's the major axis divided by 2, and that's related to then P over 1 minus E squared. So those are elliptical orbits, but you can also have hyperbolic orbits. Those are the ones with positive energy. Those correspond to E greater than 1. In that case, A, the semi-major axis, is negative, which you say, well, how can that be? But of course, this is a case where there is no semi-major axis because the orbit isn't closed. It's a scattering orbit. But P is well defined. Remember, P is related to the angular momentum. So P is perfectly well defined. Again, E is greater than 1. A is negative, but still P is positive and well defined. In that case, of course, you find a place where, for a given angle F, since E is greater than 1, there's an angle F where this vanishes, right? And that means that R must be infinite. And where that occurs has to do with the arc sine of 1 over E. And so by looking at the two places, the two phases where this vanishes, you can calculate the angle, the change in angle in this scatter when the body approaches our body and then goes back to infinity, and the difference in those angles is pi minus 2 arc sine 1 over E. So that's something you can work out for hyperbolic orbits. And here are just some relationships that you can derive for the two-body problem. You've probably seen some of these before. R dot, the rate of change of the radius, the separation is h times E over P. Sine F, it has to be proportional to E because in the circular limit, R dot is 0, so it's proportional to E. It's sine F, it's 0 at pericenter and apocenter. That's the turning points. V squared is given by this expression or by that expression. The energy is related to the semi-major axis. If A is positive for a bound orbit, energy is negative. If A is negative for this hyperbolic orbit, energy is positive. That all makes sense. E itself can be related to the energy and the angular momentum by this formula. And the orbit, for the closed orbits, the orbital period is given simply in terms of a cubed over g times m. And this is Kepler's third law that related the period of the orbits of the planets to the semi-major axis of the orbit of the planets. Right? And then there's a whole other way of formulating these equations in terms of a different variable, not instead of f, the true anomaly, this variable is called the eccentric anomaly. And there the equations take on a slightly different form, and you can relate f to u in a certain way involving tangents and blah, blah, blah. This is often used in celestial mechanics as a good, useful parameterization of orbits for the two-body problem. So it's just one of many different ways that you can describe the orbits. So any questions or comments so far? So it's just this variable u. You notice that it's sort of like the true anomaly. It's related to the angle. Remember, f was phi minus omega. So u is related to this in a similar way, but when f is 0, when you're at pericenter, u is 0. Okay? When f is pi, then u is pi, because both are infinite in that case, because it's f over 2. And this transformation gets very ugly because, of course, the tangents have bad behavior at pi over 2. But still, you can write. So it's 0 at pericenter, it's pi at apocenter, but between the two, it varies just slightly differently than f because of this very kind of complicated relationship. So it's the nice thing about u is it has a very nice relationship with time t. It's almost linear with t with this correction depending on the eccentricity. So, but why it's called eccentric anomaly, I have no idea. It's again a name that goes back to the 19th century. So you remember we've put our system on the xy plane, right? And so with this parameterization, and we measured the location in the orbit from the x-axis, so pericenter would be phi equals 0, would be, well, no. So the pericenter angle would be given by omega, measured from the x-axis, and so an eccentric orbit would look something like this. So this would be pericenter. Remember, f is equal to phi minus omega. So if that's phi, then this is f. U is a different thing. U is a little harder to draw, but f has a nice. And so pericenter is here, f equals 0, or phi is equal to omega. And then apocenter, whoops. Apocenter is out there when f is equal to pi. And omega tells you then how this orbit is oriented relative to the x-axis. Okay. Other question? Now, you see that there are a number of constants in this problem. There's h, which is the angular momentum. We know that's constant because of L is conserved, and also the direction of the plane. The vector is also constant. The orbital plane is fixed. And that just comes from the fact that we're dealing with a spherically symmetric problem. Right? Symmetry under rotations tells us that the plane has to be fixed and angular momentum has to be constant. So these are constants of the motion related to a fundamental spatial symmetry. A, or P, is another constant. And that's related to the fact that this potential does not depend on time. There's a time translation symmetry, and so energy must be conserved. And in the two-body problem, energy is proportional to A, 1 over A, and so A must be constant. So again, that's a kind of geometrical symmetry. The symmetry under time translation tells you that E is conserved, and so A must be a constant. So we have A, E, the orbital plane, they're all fixed because of these basically geometrical symmetries. But what about this constant? Where did it go? Omega, this angle of pericenter, it's also a constant. Where does that constant come from? It's a conserved quantity, it's a constant of the motion, and usually a constant of the motion is associated with a symmetry in dynamics, right? You always know this. But there's no, we've used up all the geometrical symmetries, rotation and time translation. Where does this come from? It turns out it's a very different kind of symmetry. It's a dynamical symmetry. It's a kind of a hidden symmetry that's unique. It comes about because this is a 1/r potential, okay? It comes from the deep dynamics of the problem, not just from the symmetries associated with spherical symmetry or time. It turns out that if you look at the two-body Kepler problem, you can construct a vector called the Runge-Lenz vector. There's what it is. It's V cross H. H is the angular momentum vector over GM minus the unit vector. If you take that thing and take its time derivative and plug in the two-body equations of motion, wherever you see dv dt, there'll be one there and there'll be one when you take dh dt. Well, in this case it's constant. But when you do all that, you'll discover that A dot is 0. It's a constant of the motion. And when you actually work it out in detail using the solution that we got in terms of the true anomaly for all the various variables, r, v, whatever, it turns out that it is a vector with size e, with magnitude e, and whose direction is in the direction of the pericenter. So this is A. It points toward the pericenter with a magnitude e. It's not it doesn't have the radius of the orbit, but its size is proportional to the eccentricity of the orbit. And this symmetry, and it really is crucial that you have a 1/r potential to get this constant of the motion. Turns out that this constancy of the pericenter, or this Runge-Lenz vector, is exactly the same phenomenon that's responsible for the degeneracy of the hydrogen energy levels. You know, in the pure hydrogen atom, the energy levels are characterized by a single quantum number, right? N equals 1, 2, 3, 4. And for each n, all the different L values have the same energy, right? So n equals 0, of course, is an S state. But for n equals 1, there's a P state, 3 P states, and an S state. They all have the same energy. They're degenerate. That degeneracy comes from exactly this same symmetry. And it's a dynamical symmetry. It really has to do with the 1/r nature of the potential. And it occurs only for the 1/r potential, and also it turns out for the r² potential for the spherical harmonic oscillator. And again, you can see it in the quantized spherical harmonic oscillator. The energy levels are proportional, are just given by h bar omega times n plus a half. When n is 0, it's an S state. When n is 1, you can have 3 P's in an S state, but they all have that same energy, and so on. It's the same a very deep symmetry. But the point is, as soon as you change your potential from 1/r, any deviation from 1/r will cause omega to change. It will induce an advance or a shift in the pericenter. And so that's what makes this omega so important. First of all, it has this very deep link to some dynamical symmetry, but the slightest deviation from a pure 1/r potential will cause it to move. So where might such changes come from? Well, if you're moving in the field of a body with multiple moments. Remember, the potential now has 1/r cubed, 1/r fourth. It has pieces that deviate and also depend on direction. That'll do it. If you have the potential due to a distant body, a third body, that will induce terms that violate the pure spherical 1/r potential. That will cause a shift. And most importantly, if you have changes from a pure Keplerian 1/r due to general relativity, that will also induce a pericenter advance. And of course, that became one of the most famous tests of Einstein's theory. So this omega really is a very important and interesting constant of the Kepler problem, but we'll see that it changes generally in perturbed Kepler problems. Okay. Now, in the pure Kepler problem, we noticed that angular momentum was constant, the orbital plane was fixed, so we just rotated our orbital plane, our coordinate system, to put the plane in the xy plane, and life became pretty simple. But now in general, we're going to want to look at more general problems like a two-body system, two bodies orbiting each other, but perturbed by a third body, for example. Well, now the orbital plane may become important. It may be that the angular momentum will change because of the perturbing influence of this third body. So we have to really consider our system with a generic orbital orientation. Okay? And this is often not done in sort of undergraduate textbooks, but now it becomes crucial if we want to really consider more general problems. Or if your body has a multiple moment and the symmetry axis of the body is not perpendicular to the orbital plane, if it's tilting in some direction, again, the relationship between those two directions can be important. So we really need to think about how to describe orbits in general, not just orbits on the XY plane. And there's a set of conventions that have been worked out, ever since the 19th century for how to describe such generic Keplerian orbits. And here's how this description works. So first you have some kind of reference plane that you've set up for yourself. There's the XY plane here and a z-axis perpendicular to that plane. So that plane can be anything. In solar system dynamics, it could be the ecliptic plane, the sort of average plane or the plane of the Earth's orbit, which defines the average plane of the solar system. But many of the planets are actually inclined slightly relative to the Earth's orbital plane, so those inclinations matter. So for solar system dynamics, it's typically the ecliptic plane. If you're concerned about satellites orbiting the Earth, just geo satellites, then it's the equatorial plane of the Earth. That's the most useful plane to use to define those orbits. If you're looking at orbits, say, of binary pulsars, then the orbital plane that's the most useful is the plane of the sky. So XY plane is defined on the plane of the sky, and the Z direction is the direction pointing toward the Earth from that plane. So again, it depends on the context, what plane you use, and that's your choice. Once you've made that choice of reference plane, then you define the orbit. So the first thing you do is define the orbital plane. So you take, the plane might be inclined relative to your reference plane, so there's an inclination I. But how you do that rotation depends on the direction of the rotation, and so there'll be a line where that orbit plane intersects the reference plane, okay? And so it depends on how you've done your rotation, this one or that way. So there'll be line of intersection. That's called the line of nodes. And the angle of nodes, omega, is measured from the x-axis, okay? And the convention is it's the angle of the ascending node. It's the angle, you might ask, is it this one or that one? It's the one where the orbit is going from below the reference plane to above the reference plane as the orbit evolves. So as it ascends from below to above the reference plane, that's where the ascending node angle is. Okay? So there's omega, describes kind of the orientation of this plane about z. I gives you the orientation of the plane about the reference plane. So that fixes the plane. Then in this plane, you have an elliptical orbit. And just as we had here, omega was the angle from the x-axis to the pericenter of the orbit. Here, omega is the angle from the line of nodes to the pericenter measured within the orbital plane. Okay? So that defines omega. E, of course, is the eccentricity of the orbit. That's just defined by the shape of the orbit. And A, the semi-major axis of the orbit, is, just as you expect, the semi-major axis, half the major axis of the orbit. And fine. And all of these variables that I've defined to describe this general orbit can be related to the variables that we've been using. So for example, I was the inclination, but cosine I is really clearly the unit vector defined by the angular momentum dotted into EZ, right? Angular momentum points perpendicular to the orbital plane, so it's perpendicular to the orbital plane, so the dot product between that and Z is the cosine of the angle of inclination. Okay? So I've described it geometrically, but in fact, it can be related mathematically to this particular dot product, which depends, remember, h is r cross v divided by the magnitude. It's a unit vector. So you can define cosine I in terms of variables of the orbit. Similarly, cosine omega of this line of nodes, you can show as h dot ey divided by sine I. So basically, cosine omega sine I, taking this into account, you can convince yourselves that it's just h dot, this vector dotted into the y-axis. Okay. The angle of pericenter, well, you remember we defined A was equal to the pericenter times E, so sine of omega, so A points like this. So if we dot A into this should be a capital Z, A into EZ, then it's proportional to the sine of omega, because we're looking at EZ now, not this direction. We're going in this direction. There's a sine I involved, and you have to divide by E, because remember, A is proportional to E. So you can show that omega is given by this thing, and remember, A is defined in terms of V and all the variables of the problem. The eccentricity, we already saw, was the magnitude of A, and the semi-major axis from an earlier formula is given by this expression, but again, all defined in terms of variables related to x and v. Then there's one final variable that we won't encounter very much. You really care about it only if you really worry about evolution of orbits as a function of time. And it's called the time of pericenter passage. And so it's basically t minus the integral from 0 to f of this quantity, df. F is the true anomaly. So when f is 0, little t is equal to t. So you're at the time of pericenter passage. F equals 0 is pericenter. So it somehow relates all these variables to actual time. And the point of going through all this is that these 6 variables, I mean, it should ring a bell to you that there are 6 variables, because this is the ultimate dynamical problem is a second-order differential equation in terms of x and v. And so you need 6 initial conditions to solve this problem. So you need 3 components of x and 3 components of dx dt to solve the general problem. So there's 6 fundamental variables, 6 initial conditions you need to do this. Or you might say it's a 6-dimensional system, right? Well, we've taken these 6 variables, and we're able to define these 6 in terms of the fundamental variables x and v of this problem. So a description of the orbits in terms of these 6 variables is completely equivalent to the initial conditions x naught and v naught. In fact, in the pure Kepler problem, where these are all constants of the motion, we've already seen this, these are constants. You can show that this is actually a constant too. All these constants can be directly related to the 6 initial conditions that establish the orbit. Right? But it's very useful that we can write these quantities that describe the details of the orbit in terms of x and v, because we shortly want to turn to not the Kepler problem, but the perturbed Kepler problem, okay? So now we want to be more general. We want to consider a case, a situation. So were there any questions about this, this description? But now we want to be more general and consider the possibility that our equation of motion in our 2-body system could have some perturbations, a perturbing force. I will call it a force. Again, this is the terminology used in a lot of textbooks in celestial mechanics. They call it a perturbing force, but it's really an acceleration. but they use the word force, and just to be consistent with other books, I'll use this term, but just keep in mind it's really an acceleration. So there's a disturbing force. Not a pure Kepler problem, but a disturbing force could be due to general relativity, third body, multiple moments on each of our bodies, who knows what, all kinds of things. Could be a non-gravitational force, solar wind pressure on a satellite orbiting the sun. I mean, all kinds of things. Atmospheric drag in an Earth orbiting satellite. So this could include lots of different forces that are disturbing our simple two-body problem. And the way to attack this problem is the following. It's to not look, to kind of think of the two-body problem in a slightly different way. To define, here might be the actual orbit undergoing some rather extreme gyrations. Any piece of that orbit at any moment of time, say here, our two-body system has a particular values of x and v, right? 6 variables, 3 x's and 3 v's. At that moment of time, we could translate those variables into a pure Keplerian orbit, which would be this orbit, that has the same x and v's as our orbit of interest at that time. And that translation comes by just using the things we had here. We define an orbit that has the same x and v's as our true orbit by defining the separation to be r times the unit vector. The unit vector is given by this in terms of the true anomaly, the pericenter angle, the angle of nodes, the inclination. So this reflects both the orientation of the orbit and the phase of the orbit. The radius is given by p over 1 plus e cosine f. This is our solution for the two-body pure Kepler problem, but we're assuming that r is given by this at this moment of time. P is given by this, the semilatus rectum. Our angular momentum is given by this. The velocity is given by this. Lambda, h are the three, it's a triad of vectors orthogonal to each other that are all related to the orientation of the orbit and the phase at this moment of time. So at this moment, there is a Keplerian orbit, pure Keplerian orbit that is tangent to the orbit of interest because it has the same x and v at that moment. Look at a later point of time, our orbit has gone to somewhere else. Now, say over here, but it's been perturbed by all these forces, but still, here we could associate this point of the orbit with a different pure Keplerian orbit with different values of the various quantities that appear, omega, e, p, and so on. Each of these orbits is called an osculating orbit. Osculating comes from the Latin, the word to kiss. So the two orbits are just kissing each other, they're just tangent, hence they're osculating. So there's one osculating orbit and another osculating orbit. And so instead of trying to describe this actual orbit in some complicated way, you describe it by a sequence of pure Keplerian orbits in which E, P, omega, big omega change with time. Okay? Those 6 orbital elements here will be different from the ones there in general because of these perturbations. What makes this a useful approach, however, is that when these perturbations are small, and they typically are small compared to the dominant two-body acceleration, these variations of the elements, omega, omega, I, and so on, the changes from here to here are small. So each thing is a Keplerian orbit, momentary Keplerian orbit that evolves slowly by very small amounts. E will change by a small amount, omega will change by a small amount from here to here. And so it turns the problem from trying to solve this second-order differential equation for x and v, including these complicated perturbing terms, into a set of equations that we're going to derive that will allow us to determine the evolution of these orbital elements. Once we know how they evolve, we can plug them into these formulas, and we can learn what's r, what's the velocity, what's the position of the orbit at any moment of time, because we know we can construct that orbit from the time-varying values of these orbital elements. Okay? So that's the fundamental idea of this treating this perturbed Kepler problem with orbital elements. want to check. There's something blocking the number here. Say OK. Okay. So how do we do that? Well, we take literally what I've just said and see if we can find a way to connect this perturbing force with the rate of change of the orbital elements. So there's our acceleration. And I'm going to give one example and then just state these so-called Lagrange equations that we will drive. I'm not going to drive them all, but I'll just we'll look at one case and then one of the simplest case, but the others can also be derived simply. Okay, so instead of a Kepler problem, we have the Kepler problem plus this new force. It's in general a function of r, v. It could even have explicit time dependence. So, for example, we know that the angular momentum is r cross v. What's the rate of change of the angular momentum? Well, it's r cross dv dt, right? Because otherwise you'd have v cross v, and that's 0, but it's r cross dv dt, or r cross a. The Kepler part gives 0, because it's r cross r. That, of course, you knew because it's spherically symmetric. Angular momentum is conserved. But now we have this perturbing acceleration, and so the rate of change of angular momentum is r cross f. So angular momentum may not be conserved anymore because of this external perturbation. What about A, the Runge-Lenz vector? Here was its definition. Now we calculate its rate of change, and it turns out that, again, with the pure Kepler part, you get 0. But with the non-Kepler part, the perturbation, turns out that you get f cross h plus v cross r cross f. Okay? You can work that out. It's pretty straightforward. Okay? So this tells us how these two variables, remember this gives us is related to the orientation of the orbit, and it's related to P, the semilattice rectum, and this is related to E and the line of node. So 5 of the 6 orbit elements, and T, big T we're not going to worry too much about. So this really has all 5 orbital elements that we care about built in, and this tells us how they're going to change with time. So yeah, we're in good shape. The next step is a conventional one. You decompose this perturbing force into a piece that's radial along the direction between our two bodies, something called in-track, that some celestial mechanics people call it. So it's a part of the perturbing force that's in the direction of motion. So n is the separation, lambda is perpendicular to that, so it's like in the direction of motion. And then there's a piece that's cross-track, or out of plane. It's a piece that's in the direction of h, perpendicular to our orbital plane. Since this is a function of r and v, it's not difficult to just do that decomposition into these 3 vectors, which we know we've defined them already here. So we know exactly what they are. So for a given f, you can compute these 3 pieces, radial, s, and w perturbing functions. Okay, so what is h dt, the rate of change of angular momentum? Well, it's r cross f, and there's f. Well, what does the first term give? This is the radial, this is the separation vector, and this is the unit separation vector. So what's r cross n? 0, right? It's r cross itself, basically. So the radial piece gives nothing. Then we have r cross lambda. Well, r is proportional to n, so we have n cross lambda. Well, what's n cross lambda? So there's n, and there's lambda, and this is my right hand, luckily. So it's h. So this will give s in the h direction. So there it is. And there's a factor of r, because this is r, not the unit vector. So do we get that? And then we have w, and we have r cross h. So what's r cross h? R cross h minus lambda, because lambda is going this way, and it's r across h, so it's minus lambda. So we had minus w times lambda, and again, a factor of r from there. So the rate of change of angular momentum comes from two pieces. Any disturbance in the radial direction doesn't affect the angular momentum, right? There's no torque, radial force. If there's a tangential force, that's going to change the angular momentum. And if there's a force perpendicular to the plane, it may not change the magnitude, but it'll change the direction of the angular momentum. It's going to tilt the orbit. Okay, so clearly these two pieces, W is going to, the HDT is going to have pieces in nothing in the radial direction, but in the two perpendicular directions due to these two torques. And then you can do the same thing for dAdt, and I won't go through all the details, but you can just figure this all out. You can do the same kind of calculation to see that this thing has three pieces. There's a radial piece, there's a piece in the direction lambda, and also a piece out of the plane, depending on the values of these various disturbing functions. All right?
What do they say lambda exactly?
So lambda, so the definition is back here. So we have this radial vector that goes to our orbit, and we've defined the orbital plane. So lambda is a vector perpendicular to the radial vector, but that stays in the orbital plane. So in fact, maybe on this picture. So yeah, so here, our body is here in the orbital. That's the location of our body current, of our separation vector. I mean, this is an effective one-body problem, remember. So our separation vector points here. So there's n, a unit vector in the radial direction. And there's lambda. It's perpendicular to n, but it's still lying in the orbital plane, right? And then h is the cross product, is perpendicular to those two, because that's a radial w lambda in the orbital plane, and then h out of the orbital plane. Okay, so you can see that the perturbing acceleration that's parallel to lambda So this thing changes the angular momentum in the h direction. Well, that's right, it's a torque. So it's increasing the magnitude of the angular momentum. So it's changing the angular momentum in its own direction, which means it's changing its magnitude. It's getting bigger or smaller. This is right. If you have a torque this way, speeding up the thing, the angular momentum is going to grow. So this is in the direction of h itself. But this is in this thing that comes from the perpendicular perturbing force. This is in the direction of lambda, so it's telling you that h is changing in a direction perpendicular to itself. In fact, in the lambda direction. That's changing the orientation of the orbit. So this changes the magnitude, that changes the orientation. In this case, it's a much more complicated story, so partly because this A doesn't have it has a bit of a geometrical meaning, but it's not as obvious as angular momentum. But anyway, there it is. You can work the details. It's a little more messy. But let's just use this very simple case of the torque, the change in h, to get an equation for the evolution of at least one of these orbital elements. So for example, the magnitude of the change in the magnitude of h is just r times s, right? Because this is the change in the direction of h, so it's just changing its magnitude but not its direction. So h without a vector symbol, it's just h, magnitude of h dot is r times s. So that's pretty clear. So let's look at this quantity. Let's look at h cosine I. So it's the magnitude of the angular momentum times the cosine of the inclination. And we know that, and d by dt of that is just h dot times ez. Remember, that's how we defined it. Ez is our reference z. That doesn't change. So d by dt of this is h dot dotted into the z reference direction. Well, the left-hand side, if I do that, that's just h dot cosine I minus h di dt times sine I, right? On the left-hand side, we have h dot. Well, we know what it is. There it is, dotted into EZ. So it's minus r omega w times lambda dot EZ, and if you look up the definitions from before, you can see that that's given by that. You just have to look up those formulas. And then there's this, this term, h dotted into EZ, so there's an r plus rs, and h dotted into the z reference direction is just cosine I, so there's cosine I. Okay? Now we can simplify this equation right away. How can we simplify it? Sorry? So what are you referring to this? Yeah, so this, given that, h dot cosine I cancels that, right? They cancel. Okay, so now we have a nice equation that gives us the evolution of the inclination of the orbit, di dt. Divide through, and we get a formula for di dt in terms of the w, the h coefficient, the h component of the disturbing force. And remember I said, this force acting out of the plane is going to tilt the orbit, cause the orbit to tilt some more, and then we get exactly that. This is giving us a variation in the inclination. And so we've derived the first equation for the variation of this orbital element. But again, just using the basic definitions of these orbital elements in terms of these two vectors, and then in terms of components of our disturbing force plugged into the equation of motion. Now you can do that you can do the same thing for omega, which remember was related to h-e-y. So you can take the y component of these equations and manipulate and do a little bit of algebra, and I'm not going to do it. I'm just going to then jump to the final answers, which are these. So here are this is the equation we just described. The I dt proportional to w. There was a cosine omega plus f. There's an r, which is p over 1 plus e cosine f. What else is there? And what else do we need? Oh, and then there's an h. And h is related to the square root of m times p. This is a useful formula. So h squared, remember, was equal to m times p, the semilattice rectum. So we divided by h, so that has to be taken into account. And when you look at that, then you can see this is exactly what you get. Okay? And then you could go on and find the rate of change of the line of nodes, d omega dt. Very similar, again, just determined by the perturbation out of the plane of the orbit. That changes the orientation of the orbits. P is related to the magnitude of the angular momentum, h. So dp dt just depends on s. That's the torque, the perturbing force in the plane of the orbit. So this is the rate of change of angular momentum, essentially. It's useful to use p for this, not h. So just s affects that one. Eccentricity is affected both by the radial and the tangential force. And finally, the pericenter angle changes due to a combination of all three forces with various coefficients. But as we'll see, in most cases where the perturbations are small, these changes are small. And so you can solve these equations using perturbation theory, for example. If these changes are going to be small, then, for example, you could try to just integrate this equation by plugging in constant values on the right-hand side for the orbital elements as a first-order approximation, and then you just integrate with respect to time. You can actually convert these into d by df, so you can integrate with respect to f if you prefer. So you can do a simple kind of perturbation theory using these equations, because to lowest order, remember, these variables, E, omega, I, and so on, are constants of the motion for the pure Kepler problem. So the zeroth order solution is that all of these things are zero. If you have no perturbing force, these time derivatives vanish. But if you do have a small perturbing force, then these things are still small, so you can put in constant values on the right-hand side as a first order approximation and then solve. If you want more accuracy, you take that solution and plug it back in and then integrate again. And you can go to higher orders if you wish. Okay. So just some comments about these equations. These are exactly equivalent to the original second-order differential equations. We have 6 first-order differential equations. I haven't shown there's another equation for d capital T dt that I'm not showing. It's kind of complicated, not useful, but there's a 6th one. But these equations, 6 first-order differential equations in time, as written, are completely equivalent to the 3 second-order differential equations of the perturbed Kepler problem. You know, dv dt is equal to some acceleration. So we haven't made any approximations at this point. It's just a transformation of the problem in one formulation to a very different formulation in terms of different variables. It's very similar to what you do in applied mathematics, where you have a system with, say, a harmonic oscillator with a driving force that changes the frequency. You know, you sometimes try to solve this with a trial solution, which is a sum of sines and cosines of the fundamental frequency, but with amplitudes that vary with time. And you try to find equations for those amplitudes as a function of time. And again, those equations are exact, just like the original ones. But then, of course, you make some approximations. If the frequency is high compared to the time scale over which the frequency evolves, then you can approximate and get very good solutions for those time-varying amplitudes with some approximations. But again, it's often called the method of varying constants or something. That's used in lots of places in mathematical physics. If the force is 0, those orbital elements are constants. You're back to the pure two-body problem. If they're small, if those forces are small compared to the dominant two-body acceleration, again, you can start to use perturbation theory to find solutions of those equations. The one important result of those equations is that when you integrate them, you can get 2 kinds of terms. Notice there are terms that vary on an orbital timescale, cosine f. F runs from 0 to 2 pi, so there are lots of periodic terms. But if you integrate, say, over an orbit, you may discover that some of these things don't return. They're not purely periodic. They actually have a net change from one orbit to the next. So omega may actually grow secularly with time. It will have periodic variations, but it actually changes from one orbit to the next and grows on a secular basis. So the solutions to these equations can have both periodic and secular changes in the orbital elements. And this is just a technical point about this conversion. If you like to work in terms of true anomaly versus time, then you have to be a little careful about that transformation. But this additional term that I point out here is really only important if you're doing higher order perturbation theory. And so generally speaking, you won't have to worry about it. Okay, so I think the next thing we're going to do, and we'll do it tomorrow, is take this kind of machinery, this osculating orbit, perturbations of the orbital elements. These are sometimes called the Lagrange planetary equations because they were worked out by people like Lagrange in the context of solar system dynamics. We'll take these equations and then apply them to some real problems of 2 bodies perturbed by a third body, 2 bodies perturbed by a body with a quadrupole moment, and so on, to see what kinds of perturbations of orbital elements actually come out, and there are some real-world applications of those results. So that'll be tomorrow, same time, tomorrow morning. Okay.